So looking at this example problem, a compound with a molar mass of 104 grams can be reacted with hydrogen using palladium on charcoal as a catalyst, and it's seen to absorb 4 moles of hydrogen gas. When the original alkyne compound is further reacted with ozone with a zinc catalyst, there's only one product produced, succinic acid C4H6O4. Write any relevant chemical reactions and the structural formula of the original alkyne. So let's start with that 104 grams per mole information. Of course, we can take a molar mass and turn it back into a chemical formula because the majority of hydrocarbons is made up of carbon and hydrogen in a 1:2 ratio. So 14, the mass for CH2, we can divide that molar mass by 14 to work out roughly how many carbons and hydrogens there are. That would give us a value that goes into the original molar mass 7 times, leaving us 6 units of mass unaccounted for. That would be too much mass to turn into hydrogen. C7H20 would go beyond the saturation limit. But we could use that 6 grams together with 6 grams of mass from this formula, dropping the hydrogen count by 6 to get a chemical formula that fits the molar mass of 104 grams. That would be C8H8. That comes to 104 grams per mole, and it fits within the limits of our saturation point. Speaking of which, that saturation point, with 8 carbons in the main chain, we could get double plus 2 the amount of hydrogen, which potentially would make for a total of 18 hydrogen. And we know that for every 2 hydrogens missing from the chemical formula, it suggests either that there's a pi bond or a ring structure to the molecule. So 10 hydrogens missing, and 2 hydrogens at a time for either a pi bond or rings. Of course, we know from the original question that this alkyne reacted with hydrogen and absorbed 4 moles of hydrogen gas, H2. For every mole of hydrogen gas absorbed, it suggests the presence of a carbon-to-carbon pi bond. So 4 pi bonds are explained, and the last set of hydrogens from our missing 10 hydrogen count can be explained by a ring. So we must have some kind of ring structure with 4 pi bonds, and those 4 pi bonds could be used to make 2 carbon-to-carbon triple bonds. So we know a lot about our molecule already. Of course, the ozonolysis part of the reaction is taking an alkyne and breaking open that carbon-to-carbon triple bond and turning it into a carboxylic acid. So every time that pi bond breaks open, it produces a carboxylic acid on either side of the carbon-to-carbon triple bond. And because we're specifically dealing with this formula of C8H8, it means that ozonolysis reaction to produce succinic acid, a product, must be producing 2 molecules of succinic acid. Thereby we get back to 1, 2, 3, 4, 5, 6, 7, 8 carbons in the original formula. So we know almost everything we need to know about this compound now. We're producing 2 molecules of succinic acid, and when that succinic acid molecules are produced, of course, we have added on oxygen to the molecule, those carbonyl groups, as well as those alcohol groups. So removing those oxygens from the molecule, those remaining parts of the molecule must have been connected to each other through a carbon-to-carbon triple bond each time. So the original molecule must have been this 8 carbon cycle with 2 triple bonds, explaining the 4 moles of hydrogen which is uptaken, and the identical structure of the product from the ozonolysis means it must be symmetrical through the middle, with a carbon-to-carbon bond through the first two atoms and then through carbons 4 and 5.